Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. In the last class we have started the topic of leaching and extraction. We have discussed the basics of leaching and extraction process and few equipment that is used for leaching process, right. So, today we will discuss a very important thing, that is the equilibrium stages for leaching. Since we are covering the basics of this leaching and extraction process here, and to understand this in a better way, you need to know the equilibrium stages, and that is generally explained in distillation or mass transfer cases, but since that is not part of our course, I will try to explain a bit of equilibrium stages to you, so that you can understand how the extraction process can happen and what are the limiting cases. I mean, is the complete solute is removable from the mixture, or how mathematically we can proceed if we want to estimate that or we want to design the extraction process. Okay. So, I will try to give you some overview related to the equilibrium stages for leaching process. First we will discuss leaching, later on we will also give you the equilibrium stage concept or those diagrams and descriptions for the liquid extraction. So, considering equilibrium stages for leaching, the equilibrium data of leaching can be plotted on the rectangular diagram as the weight fraction for the three components. So, we have three components basically. One is the solute A, okay. Solute A that we want to separate from the mixture of inert or leach solid, that is B, and this process is done using the solvent C. So, A will getting mixed with the C, and this A initially is in B, which is inert. So, at the end of the process also B will be inert, maybe some part of C will be mixed with that, but ideally we want to separate A in the C. Okay. So, the concentration of inert or insoluble solid in the slurry mixture is given as follow, that is in that is equal to kg of B by kg of A plus kg of C. So, as we have mentioned that in the slurry mixture some amount of solvent will be there and some amount of some amount of solute will be there. So, ideally what happened that suppose this is a micella, solid particle is there, okay, a solid micella is there, and this I want to separate, by contacting it with a particular solvent. Okay. So, what happened that when the separation has occurred and this solid become separated, where we have mostly B, that is inert material, and this liquid which was having C, and here there was some amount of A which is solid. So, now it has moved with C plus A, and here it is B, but B was not as a dried one. Okay. So, B has some amount of C, that is the solvent, and in that some amount of A will also be there. Okay. So, in that suppose the liquid, when it becomes equilibrium, when this solvent and the solid, when the extraction or leaching process takes place, and we assume that the equilibrium stage has arrived, that means the solute was there that has been leached to the solvent, the maximum extent possible has been leached to the solvent. Okay. So, suppose in the solvent initially the concentration of A was 0, and in the solid the concentration was 50%. So, if at the end of the process suppose 45% of that A has been extracted, so that 45% has come to the come to this solvent now, right. So, when we take out the solvent, we are getting now 45% of that A. Now, whatever small amount of solvent will be associated with the B, that is the inert liquid, that will also ideally have the same fraction or same concentration of C, because whatever liquid part is there, some liquid part will be definitely there. So, this concentration of A, if I say Ca, C suffix a, concentration of A in the C stream or the solvent stream, and concentration of A in the stream that is overflowed in the process will have same concentration, right. So, this ideally we call as the equilibrium condition. So, in that process, the when we call the concentration of slurry, when we want to define the concentration of inert solid in the slurry, then N is equal to kg of B by kg of A plus kg of C. Okay. Now, in the equilibrium, we will try to see that what are the different equilibrium stages and the concentration in both the stream, that is the overflow stream and also in the underflow stream. So, underflow, this is the settled solid leaving the stage. The settled solid leaving the stage contains some liquid, as I said that the inert solid B will not go alone or in a dried form, some liquid will be associated. Okay. So, some liquid will be associated, that is called the underflow, and that liquid will have some dissolved solute as well, and overflow is the liquid containing the oil or containing the solute that is being extracted. So, that has been taken away in the overflow, right. So, the concentration of which is equal to the concentration of the solute in the liquid in the slurry. So, these two concentration, that is concentration of the solute in the overflow and the concentration of the solute in the solvent which is going with the underflow, these two will be same. Hence, this is indicated by xy plot on a 45-degree line. So, if we plot this concentration, suppose I denote the concentration of solute in the overflow by x A, and this concentration of solute in the underflow solvent, that is y A. So, this will follow a 45-degree line. Okay. This will follow a 45-degree line. We have that diagram maybe in the next we will show you. So, what it says that the composition of solute A in the liquid fraction, that is the overflow, is given as x A equal to, that means what, kg of A, that is solute, divided by kg of A plus kg of C, because the stream that is going in the overflow will have the solvent as well as the solute. So, kg of A plus kg of C, in that what is the fraction of kg of A, that is the solute. So, that is x A, and similarly the composition of solute A in the liquid fraction, that is the underflow, that is given by y A equal to kg of A divided by kg of A plus kg of C. So, we can observe that these two are same, one stream that is going out and the same stream, some fraction, some part of that stream which is going in the underflow with the solid. So, that has this concentration. So, x A and y A ideally should be similar or should be same. Now, a single stage leaching process, when we consider the single stage leaching shown in a rectangular diagram. So, let me first show you that single stage leaching diagram. Yes, we will go back to that slide. First, we will see what happened in a single stage. Okay. So, let us see, this is a single stage leaching is occurring. So, we have the slurry solution which is entering, the feed solution or slurry solution, and we have solvent which is entering. Okay. Then this solvent will take some fraction of the solute and then it is moving out, and this slurry which is again coming out as a slurry from the first stage, right. So, V represent the kg of solvent that is entered, L represent the kg of slurry that is entered, N 0 representing the concentration of inert solid, Y 0 representing the concentration of the solute in the feed slurry. Okay. Similarly, Y 1 representing the solute concentration in the outgoing slurry, and x 2 and x 1 or x, these represent the solute concentration in the solvent. Okay. So, this is the single stage thing, and now we will see that we will go little back. Okay. So, we were here. So, in a single stage that we have seen, okay, in a single stage where L is the slurry entering, V kg per hour, that is the overflow solution with composition of X A, L kg of the liquid that is in the slurry solution with composition of Y A. Okay. And so, like that any notation you can give to them, x A 1, x A 2, like that. So, whatever. So, overflow solution with composition of X A and L kg per hour is the liquid slurry solution with composition of Y A based on the given flow rate of B in kg per hour of the dry solute free solid. So, B here is the dry solute free solid, in that term we are taking B as an inert. Now, the equilibrium diagram when we try to make, what we will do is we represent, we will draw a square plot, in that this bottom axis x axis represents N versus X A. So, initially N means the inert solid concentration of the inert solid in the in the total slurry, that is kg of A by kg of C. So, in that the concentration of solute the concentration of the solute, if we consider, that is Y A, and X A, that is the concentration of the solute in the solvent stream. So, X A will be 0 initially compared to this N, and as it moves the other direction, it is increasing, because from 0 to all the solute fraction from the inert solid or slurry, it is going to mix with the solvent. So, eventually X A will increase from 0 to 1, the maximum fraction will come out, whereas the upper curve that show the underflow, that means this is N versus Y A. So, what happened that initially Y A was 100%, okay, Y A. So, the fraction Y A will be 1.0. So, initially this was higher, and as you know the slurry is getting mixed with the solvent and the solvent is taking the solute away. So, it is decreasing, okay, Y is decreasing and X A is increasing, right. So, ideally if it happens that the concentration X A equal to Y A, because that is the ideal case, on in the equilibrium situation this should happen for ideal extraction. Okay. So, those two concentration X A and Y A are same, and this we have discussed already. So, in that case the tie lines are vertical straight lines. So, when we plot Y A versus X A, we will get a straight vertical line. Okay. So, this is 45 degree line. Now, what will happen that if suppose there is a deviation in the concentration of X A and Y A. Okay. So, that means whatever concentration was there in the slurry or in the feed solution has not fully gained by the solvent. So, there is always some gap. Okay. So, in that case we will not get the straight line as the operating or operating line. So, in that case we will get a little curve as an operating line. So, that represent this will be your the concentration of Y A and there will be the concentration of X A. Okay. So, we can get this kind of a plot. When the tie lines are not vertical, that means there is a deviation between the X A and Y A. Okay. So, next is single stage leaching. Now, we will do the material balance. So, this is our figure, if you remember that we have L 0, N 0, Y 0 and B that is entering, and here V 2 X 2 that is entering. Here V 1 X 1 that is leaving stream, or this is the overflow, and this is the underflow, that is L 1 N 1 Y 1 B. Okay. So, considering that if single stage mass balance we want to see overall. So, a single stage liquid extraction are as follows for total solution balance for solute A and solvent C, because if we know those two, the other can be easily calculated. So, a component balance on A and a solid balance on B that can be given respectively. So, the total balance will be L 0, that is the feed stream, plus V 2 solvent, that is equal to L 1, that is the feed slurry that is outgoing, or this is the underflow, plus V 1 which is the overflow. So, this will be M and this will be constant. Now, the solute concentration in the feed slurry is Y 0. So, Y A 0 into L 0 plus the entered solvent stream, if the solute concentration is having X A 2 there. So, V 2 into X A 2, that will be equal to L 1 into Y A 1. So, this is the underflow that is going. So, L 1 into Y A 1 plus overflow, that is V 1 into X A 1. Now, this will be together coming as M into X A M. Okay, M into X A M. So, this is because when these two stream is getting mixed. So, let us say the separation will happen up to a certain point, which is signified by the point M, when the equilibrium will be reached. So, that M, the position of that M point we need to find, so that we can predict that what will be the extraction efficiency or what will be the separation, what fraction of the separation of solute has been done. So, M into X A M is required for that. Now, if you want to do balance on the inert material, that is B. So, B will be how much? Initially the stream L 0 has a concentration of N 0 for the B, and the solvent did not have any trace of B. So, the total B will be equal to N 1 L 1 plus 0, that is N M into M. Okay. So, then for a single stage case, as I mentioned, that M will be the total flow rate in kg of A plus C per hour. X A M and N M are the concentration of the point. X A M and N M are the concentration of the point. So, if suppose we had initially we had L 0, that is the feed slurry, and we had V 2, that is the solvent. We had some X A 2 for this V 2, and we have some Y A 0 for this L 0. Now, when these two streams are getting mixed, they will come to an equilibrium at certain point M, let us say. So, that M, from the M again, if we consider that, there will be V 1, 1 point V 1, that indicating our overflow, and that will have a concentration, and here again L 1, that is our L L1 is our slurry that is going out. So, this will be the equilibrium point. Now, they corresponding to this equilibrium, what will be the Xm and what will be the Nm that we find. So, that we can get what will be the bulk liquid there and what is the concentration of the solute. So, X A plus X C that is equal to 1. Similarly, Y A plus Y C equal to 1, because A and C both are the components of the solution plus solute mixture. If one fraction we know, the other can be fraction can be calculated with considering both the fraction equal to 1. Now, L1 M V 1. So, the line L1 M V 1 and L0 M V 2, these two are straight line and the point M is the intersection of these two line. Okay. So, they has to reach to this point for equilibrium. So, in a single stage leaching, we will solve a problem, so that we can see that how we can draw this equilibrium diagram and how we can calculate that what fraction will be extracted by the solvent and what will be retained. So, in a single stage leaching of soybean oil from flaked soybean with hexane, 100 kg of soybean containing 20 weight % oil is leached with 100 kg of fresh hexane solvent. Okay, 100 kg of soybean was there containing 20 weight % oil with leached with 100 kg of the fresh hexane solvent. Now, the value of N, that is the inert material for the slurry underflow, is essentially constant at 1.5 kg insoluble solid per kg solution required. Calculate the amount and the composition of overflow V 1 and underflow slurry L 1 leaving the stage. So, this is our question. We have to calculate the amount and composition of overflow V 1 and underflow slurry L 1 leaving the stage. So, how we can proceed in that problem? First, we have to see we have single stage case. So, we can have that diagram. We can make this diagram where L is entering okay, and there V is coming into. Okay. So, V first is V 2 stream that is coming, that is 100 kg, but there is no trace of solute. So, X A 2 is 0 and X C 2, that is it is purely solvent. So, X C 2 is 1. Now, for entering this slurry system, so this has 20% of the oil. So, solid will be 100 into 1 minus 0.2. So, 80 kg insoluble solid will be there. So, what is L 0 then? So, the mass of the solute that is entering, that is there 20 kg. Now, N 0, that is on 80 by 20, that is 4 kg of solid per kg of solution. Okay. So, Y A 0 is equal to 1, because initially all the concentration was there in the feed slurry itself. So, Y A 0 equal to 1. Now, to calculate the location of M, that is the mixture point. So, if these two liquids are getting mixed, so what will be the equilibrium point? To calculate that, L 0 plus V 2, that is 20 plus 100, that is equal to 120. This will be our M, the total material of solvent plus solute. Then component balance, when we do L 0 into Y A 0 plus V 2 into X A 2, that is equal to 20 into 1 plus 100 into X 2, and this is equal to M into X A M. So, putting the value, we are getting X A M as 0.167. So, this is very important. So, at the mixture condition, the concentration of the solute is coming this, then B will be N 0 L 0, right, because there is no other component mixing with this. So, this is inert. So, N 0 L 0, that is equal to 4 into 20. So, 80, and this 80, this B 0 N 0 equal to N M into 120. So, N M also we are getting as 0.667. So, now the point M is plotted along with the V 2 and L 0. So, how we can plot? It was given that initially when V 2 was when V 2 the concentration of x A 2 was 0 and the concentration of y this was at 1. So, L 0 we have taken from here and this was corresponding to the 4 kg of the solid per kg solution. So, there is 4 kg of per kg solution. With respect to that the concentration y A 0 was 1. So, this was the initial point. Now, it says that that n has to fixed at 1.5. So, this is this line showing. Okay. And when this line is getting mixed, so this has to, because two stream are coming, the L 1 stream and V 1 stream. So, this line has to pass through this point. Okay. So, this will be the M or mixing point, for which N M will be 0.667 and the X A M that will be 0.167. Okay. So, solving or using the lever arm rule, we can get the L 1 as 53.3 kg, L 1 will be 53.3 kg and V 1 that is the solvent, that is 66.7 kg. Similarly, we can have the multi-stage counter current extraction. So, in the multi-stage, similarly like we had earlier one stage, we have now 1, 2 and up to n stages, but the process will be same here. This is a counter current leaching. So, we have to enter solvent, from one side. Okay. So, here the solvent is entering V n plus 1 in the nth stage with x n plus 1 is the concentration and then it is moving on to stage 1 and there V 0 is coming out with x 0 equal to x 1 concentration. Similarly, L 0 y A 0, that is the the solid or the slurry phase that is entering, that is L 0 and y 0, and that is eventually coming to the end stage, that is L n y n. Okay. So, in this figure the mass flow of the light stream is denoted by V and the flow of the heavy stream by L, that means heavy stream in the sense that is the slurry solution, and the concentration in the light phase by x and the concentration in the heavy phase by y, as we did for earlier cases as well. So, then we have to do the material balance for the multi-stage multiple stage counter current leaching. So, that will be from the from this one V n plus 1 plus L A. If you go back to the multi-stage figure, so we have V A L A x 0 y 0. So, if this is so, so this V and L n and V n plus 1 and y L A. So, this have to be balanced, right. So, V n plus 1 plus L A, that is equal to V A plus L n. Okay. So, whatever solvent entered into n plus 1 plus whatever slurry entered into the first one, that will be equal to whatever slurry came out from the n plus 1th and what is the overflow came from the first one. Then we do the component balance similarly as we did for the single stage, and finally, from these two equation we eliminate V n plus 1 So, so from the balance of the multiple stage counter current leaching, we have this equation which shows the mass balance of the solvent stream and slurry stream. Okay. And then we have component balance, that is the solvent, in that what is the fraction of the solute component and what is the component in the slurry. Similarly, what is the component in the in the overflow and what is in the underflow. So, with that we eliminate V n plus 1 and we put it in this equation, so that we can get x n plus 1, that is x n plus 1, that is the concentration of solute in the overflow stream, or we can consider this as a solvent entry for the other one. So, this can be defined by this equation, where y n into third bracket ln divided by ln minus L A plus V A plus V A x A minus L A y A. So, A stands for the first and x n plus 1 stands for the last stage or nth stage. So, this is how we can observe here. There was nth stage and there was first stage. For the first stage, the everything, that is the entry of the slurry and exit of the overflow signified as L A y A 0 and V A x A, like that, and here all are at n plus 1. Okay. So, this is the equation that we have to use. Now, in many practical cases in which the equal quantities or equal molar quantities of the carrying streams move from one stage to the other stage, that is where the flow rates are the same in all the contact stages, then for the heavier phase or slurry phase, we can consider this L n plus 1, this is equal to L n, this is equal to L A up to L, and for the lighter phase again V n plus 1, that is the solvent entered into the nth one, that is equal to V n, that is the overflow of the nth one, and eventually that is V A, that is the for the entry of the first one, entry of the solvent in the first one. So, this is the mass of the solvent that is coming. Now, a simplified equation can be written for such cases where we can take x n plus 1, that is equal to y n L by V plus x A minus y A L by V. So, this method can be applied where the flow rate from one stage to the other stage are similar. Now, once you have to understand that how the equilibrium point is determined in case of the leaching experiments, then the next stage is you have to calculate the efficiency of the leaching. So, for that the efficiency of a real contact stage is a measure of the deviation from the theoretical equilibrium condition, because theoretically we should have equal x A and y A value, but there is some deviation from that. So, stage efficiency in all stage contact process is generally expressed as Murphy efficiency, that is denoted by eta m, that equal to x 0 minus x by x 0 minus x star, where x 0 is the concentration of the extract entering the stage, entering the stage, and x is the actual concentration of the extract leaving the stage, okay, and x star is the concentration of the extract at equilibrium. Okay. So, x 0 is the concentration of the extract entering the stage, x is the actual concentration of the extract leaving the stage, and x star is the concentration of the extract at equilibrium. So, this will give you the idea of how efficient your stage performance is in case of a leaching. I mean this is true for a multi-stage leaching or single stage leaching. Okay. So, here we will stop, and in the next class we will solve a few questions on the multi-stage leaching, and we will also see the other specific cases where not only the solute, but the solid may be also required in some specific cases of food production. So, both ways we can use the leaching or extraction method, either to separate the particular solute component, or in some cases where the solid we want to get in pure form, where some impurity that is our mix with the solid material, that has to be separated. Okay. So, thank you for now. We will meet in the next class.